this afternoon session is Xi Luo. He's currently a PhD candidate at Fudan University with Professor Yongsu Wu and Janet as well.
Yeah.
Do you work with Janet?
Yeah.
Okay, cool. So he's going to talk about topology, induced emergent dynamic gate theory, and extended KMH model.
I would like to thank the organizers here who organized such a great workshop, and it is also my great honor to have the chance to talk here. So today I'm going to talk about a mechanism of the emergence of dynamic gauge theory, and that reason is due to some topology reasons of the non-trivial band structure of the fermions. And so let me first thank my cooperators, Professor Yue Yu, who's in the Chinese Academy of Science and also Fudan University, and his PhD candidate, Long Liang, but unfortunately I did not get his photo. So let me first give a short introduction. So as we may know that confinement and deconfinement phase transition in gauge theories, gauge fields are crucial in particle physics, post-particle physics, and condensed matter physics. So, for example, this QCD case here we just talked about as a joke. Anyway, the phase transition here is still a mystery. Say this is perhaps the known phase diagram of the QCD4. That is, we have the asymptotic freedom here if you are in the high UV limit. And in the IR limit, it is infrared slavery here. And well, so all those, say for example, LHC, they works at this region, and they discover this phase transition, say, from hadronic particle to quark-gluon plasma. And now there are some colliders were building in Europe and also China. They are trying to explore this area. And in this phase, there are so-called the color flavor locked phase, or in the condensed matter language, it is the so-called color superconductor. But this phase may only be realized in some neutral stars, but it is still far from experiments. So for now, there are no colliders were built for exploring this area. It is still under theoretical considerations. So all those phase transition is still a huge mystery in the real world. And also, for example, in the condensed matter physics, there are also kind of confinement, deep confinement phase phenomena. For example, the famous spin charge separation, the degree of freedom of spin and the degree of freedom of charge, they separate. And also superconductor, that you can only see the bound state of two electrons with different spin, but you cannot see the one electron. So this photo is a flying acorn above a superconductor. So you guys may know about a picture about of a poor flying frog above a superconductor on the high magnetic fields. So I was told that it should be might be a pedagogical lecture, so I may talk a little more about in the introduction. So there are two ingredients in this work. One of the ingredients is the Haldane model. Actually, we are going to talk about the so-called Kane-Mele model. It is simply the double of Haldane model. So let me first introduce what Haldane model is. It is simply a lattice model with nearest side hopping, and also the next nearest side hopping with a phase term. And also you could add a offset on each side. So it is simply on a lattice model on the honeycomb lattice. So if you along this hopping lines, they have the phase term here. So if you add this offset potential, then this will break the inversion symmetry, and it will lead to a trivial insulator. But if you add in this phase term, it will break time reversal symmetry, and then it will lead to a topological Chern insulator. So this Chern number is determined by the sign difference at two independent Dirac points. So this model has the property that it do not need external magnetic field, but it has some non-zero Hall conductance, so it is a model for the so-called integer quantum anomalous Hall effect, and the Hall conductance is related to this Chern number. And another, recently, this Haldane model is could be realized in abstract called fermionic atoms. So this is the theoretical predicted lines of the phase. In this phase, its Chern number is 1. In this phase, its Chern number is -1, and the other part are just 0. And this dashed line is the uncertainty of the lattice sites, because they are working in the optical lattice. So another ingredient of this work is the Tilly model. The Tilly model is actually the people are trying to give some bosonization in 3 dimensions. So, for example, the massive Tilly model is defined as this. You have the massive Dirac dispersion, and then you have the current induction term. And then you use the metric trick, the so-called Stirnov-Chaba transformation, that you decouple this current interaction with the extraordinary fields, A here, and then you integrate out all this fermion degrees of freedom, you get this so-called Maxwell-Chern-Simons theory. That is, in this work, they give an proof about the equivalence between these 2 partition functions. So it's simply saying that for a massive Tilly model, it is equivalent to the Maxwell-Chern-Simons theory. It is kind of bosonization in 3 dimensions. So let's go to the emergence of this Proca theory. Proca theory is simply the Maxwell theory with massive photon. So here we're talking about the Kane-Mele model. As I just said, Kane-Mele model is simply a doubled Haldane model with time reversal invariance. So it is the lattice model is like the near side hopping, and also the next nearest neighbor hopping. And this new here is defined as this. If you are in this right term, it is defined as -1. If you move this left term, it will define as 1. And this lambda is the spin orbital coupling constant. And if you solve the dispersion near the Dirac points, so that is the minimum of this band structure, you will have 9 Dirac points. 6 Dirac points, and you take out 2 inequivalent Dirac points, say for example these 2, and you will find that the dispersion near the Dirac points would be linear, so they are the Dirac fermions, and you will find that the mass gap is simply proportional to the spin orbital coupling constant, and you can also calculate its corresponding Chern number. You will find that for spin up, the Chern number is -1. For spin down, the Chern number is 1. And so also this is this Kane-Mele model is the 2-dimensional time reversal topological insulator. So it is in its SPD phase. And now we turn on the interaction. We say we use the physical current here, and this current is simply like this. It is the fermion current, and if you actually write down this J0 square term, you will find that this term is simply the nearest neighbor Hubbard interaction. So this is why the name Hubbard interaction is here. And so the story is quite simple now. The model is actually a doubled Tilly model. So you have the Dirac dispersion generated from the Kane-Mele model, and we have this kind of interaction, this current interaction. So after a Stronoff chart by transformation to decouple this current interaction, and then integrate out this fermionic degree of freedom, so we will get to this mutual Chern Lagrangian, and this nu is related to the spin Chern number here. For up is -1, for down is +1, and this alpha is the fine structure constant here, and this G square is related to the coupling here. So now, very interestingly, when the interaction U is simply the G square becomes stronger, you find that there will be some excitation in the charge gap. So now you can, for example, you integrate out this A up fields, then you will finally receive this effective action that is simply the Maxwell term and its mass term. So this action is the so-called Proca theory, and this mass term is related to the fine structure constant it's defined before. So it is proportional to the inverse of the G square, the coupling constant. But we may need to ask when it is possible for us to integrate out one gauge field. So we need to require that the spin gap becomes lower than the charge gap. So why the spin gap here is important is that because in this definition of this gauge field, we will find that this A up actually related to the spin up current, and this down related to spin down current. So its minus is actually the spin current. So sorry. So in order to get this theory, we will have to actually when you need to so let me just write this down. So as before, you have the band structure. Say we have a band gap here, and actually this is the charge gap. And there might be some collective modes here that corresponds to the spin excitation. So it's the spin gap. And in order to get this Proca theory, we need to integrate out this charge degree of freedom to, so we will need this charge gap be larger than the spin gap. And the spin gap is simply related to the mass of the Proca theory that is proportional to the inverse of the fine structure constant. So we will have this condition here. This part, it is the requirement that the spin gap should be lower than charge gap, and the coupling constant T, the Hawking constant T here involves is that we also need the linear dispersion of Dirac fermions to get that Chern term. So if this band structure is a little deviated from the Dirac structure, so it might that gap may proportional to T. So we need to have that spin gap be lower than all those gaps. So when this requirement is achieved, then we will have this Proca theory. So actually, the efforts to determine the limit of photon mass in the real world is still going on for a long time. So in that theory, we may, if it is possible to realize in experiments, so we may discover some of the phenomena if the photon has some mass. So we plotted the phase diagram with exact diagonalization of 34 sites. So in this part, it is still the ground state is still the quantum spin Hall effect, so that is still the SPD phase. But if the interaction is strong enough, it will draw a phase transition into the mod insulated phase. So this phase, it is topological trivial. But in between, there might be some collective excitations which can fulfill this Proca theory. So the finite Proca mass. So we do not have a massless theory. We have a gap theory, and this gap theory is also consistent that the bulk structure is still a topological insulator. So which means that the bulk still have a gap, and lithium. But the emergence of this gauge theory is due to the non-trivial topology of the band structure. In other words, we have non-trivial Chern number of different species of Dirac fermions, so non-zero Chern number. So this kind of mechanism is different from the emergence by the main field theory. You know that in most of the theories about the emergent gauge theory that we require some main field theory, or we consider some fluctuation around some saddle points, but here we do not need any main field theory assumption. And this kind of emergence of gauge fields is due to the non-trivial topology here. And actually, this could also be experimentally detected by some Bragg scattering. Say, for example, if you consider this is the optical lattice model, then you have to beam of light you have to beam of light with different momentum and also energy, and this term, and then hit this optical lattice, then there will be some resonance, and this will get some shift in this. You will get some shift after you absorb a photon. So this difference of time of flight will tell you the information about the dynamical structure factor here. And because we are considering some weak interaction, so we can consider at the zero temperature limit. So if you actually experimentally use this Bragg scattering, you could find this dynamical structure factor. And this dynamical structure factor is related to the density correlator, and actually it is the imaginary part of that density correlator, and you can calculate it as this behavior. So actually this kind of collective modes can also be able to detect by some experiment, some cold atom experiments through Bragg scattering. And well, now maybe we may also wonder about the zero mass limit, because in the reality, we know photon may still do not have a mass here. So we need to consider about the C tends to 0 limit or the large lambda limit, which means that we need to consider about the strong spin orbital coupling limit. In that case, we will have a compact U1 Maxwell theory, but we may need to think a little further that for this the compact here is because we are considering the system on some compact manifold. So, or I should say, the lattice model have periodic boundary conditions. So here we have a compact U1 Maxwell gauge theory. For a compact U1 Maxwell theory, we know that in two-dimensional, two spatial dimensional, we will have some monopole condensation. This work is the famous work by Polyakov, and it will induce some charge confinement. So now here we still have a gap here. That gap is related to the charge confinement. So this phenomenon can also be experimentally detected through the Bragg scattering. And in the case when there's a massless limit, we will find that the structure is similar as before, but here the mass term is simply tells us about the density of the monopole condensation. So now we go to the Emergent QED3 case. So actually, in this case, as before, we only considered about the gauge fields. So now we may add in another species of fermion that serve as the matter field in the QED3 case. And also, we may break the time reversal here. In order to break the time reversal symmetry here, we simply need to dismatch the fine structure constant. That is simply, we only need to distinguish between the hoppings and the couplings of spins will destroy the time reversal symmetry. So again, we consider this kind of interaction, current interaction. So you need to couple the extra species fermion chi with the background fermion current, and you do similarly. You do the Stranovic-Hubbard transformation. You will get an effective theory like this, and this tells us that the time reversal symmetry is broken here. It will have time reversal symmetry only if this fine structure constant are the same or they match. And this term is the emergent charge of this high fermion. So experimentally, we predict that there might be some Bragg-2 Hall effect and also quantum-anomalous Hall effect. Say, if we integrate out that chi fermion, we will again have this kind of effective Lagrangian. This is the Proca part, but also we have the Chern-Simons part. And the Chern-Simons coefficient has two contributions. One is from the Chern number of chi fermion. When chi fermion has non-trivial Chern number, then we will have the quantum anomalous Hall effect here. But when the chi fermion do not have only zero transmember, then we will not have the enormous part here. And this part is from the background fermions. So we can calculate the current corresponds, and it is a Proca equation of motion like this. So now if we again simplify all those equations, we consider a static spatial distribution of the spinful fermions. So we will have this kind of this kind of response equation. So it is quite like the Hall effect here. So we predict that this plateau Hall effect corresponds to the background fermions, and also the quantum enormous Hall effect may be observable regarding to this electric field, and this electric field is actually fulfilled by this spin density. So perhaps I started too quick. So I may come to some conclusions and discussions. I think first we considered about interacting fermions, and we also add some spinful fermions, which means that we have time reversal symmetry here. So this kind of model may be related to what Professor Chern talked about this morning about interacting fermions. And in this model, if we add in the current interaction, we will have a mechanism of emergence of gauge fields, and this kind of emergence is due to the non-trivial topology of the band structure, and also we need the Dirac fermion-like dispersion. And this kind of mechanism is totally new from the previous emergence of gauge fields through the infused theory. And also, we think this kind of phenomenon, if that is realizable in the experiment, so that will give us some kind of playground to tackle the problem of or the mystery of confinement and deconfinement phenomena, and also that this confinement and deconfinement phenomenon might be also related to some non-trivial topology of the QCD, something like that. Then, if we consider, if we add in another species of fermion, we will have the plateau Hall effect and also the quantum enormous Hall effect in the QED3 case. And it may be able to, we may able to generalize to non-abelian case. So if we add in the Rashba term, we do not consider Rashba term here, so we only have the emergent U1 gauge theory. But if we add in this Rashba term, we may have some emergent SU2 gauge theory. And this also, there might be some experimental realization for this Proca theory, because we have experimental realization for Haldane model, and it is what we consider about here is the Kane-Mele model is simply the double of Haldane model. So it may we may able also to realize the Kane-Mele model in optical lattice. And about the 4+1